Well, welcome back, guys. Allison, I see you got a partner there.
Yes, it's a new kitten we adopted.
Oh, okay. I got two of them here someplace, actually three of them. You might hear them. Anyway, welcome back, everybody. I don't see Crystal, guys, so.
Not yet.
Okay, let us continue with chapter 9, a fairly short chapter. This deals with acids and bases. Now, a while back, we were talking about one of the differences between molecular compounds and ionic compounds, and I stated that at that time that ionic compounds will, when placed in water, will dissociate into their ions, whatever they were, the positive and the negative ions. Okay. Now, those ionic compounds, which we'll learn, all of them do that. Some of them go 100% totally dissociated, some much less. And that has to do with the solubility of those ionic compounds in water. And then I also mentioned that for covalent compounds or molecular compounds, that when we place them in water, they did not dissociate because the bond between them was actually an actual physical bond, a sharing of these electrons and that bond between the two atoms. The only one exception I mentioned, or maybe not, but I mentioned now, are covalent compounds that are classified as acids. And one that's very familiar, or maybe not, but it's roaming around in your stomach right now, that's hydrochloric acid, okay? So we'll be talking about acids, and these are covalent compounds, and these are the only ones that dissociate in water when we place them in water. Now, some of them dissociate, like the ionic compounds, 100% totally dissociate, and some do not. Some much less, and that has to do with the solubility of these acids. Okay, now, if you recall from the periodic table, we place hydrogen in group 1A, and simply because it has one valence electrons like the other ones in that same group, okay? Now, hydrogen is very unique in that one valence electron, which is going back to electron configuration, is the 1s1, okay? And like the other ones, the other elements in that group, they also can lose that electron. And obviously now the net charge is a plus. So they produce these hydrogen plus ions. They have their own little name. They're called protons, okay? And they're nothing more than the hydrogen atom that has lost that valence electron, which now has a net charge of +1 because it has no negative, but it has one positive proton, so it's got a net positive charge. Now, that is what causes the acidity of material. A variety of different examples that we'll talk about. We're all familiar with acids. For example, vinegar, very acidic, very sour tasting. Okay, lemon is a good obvious example. So they are very corrosive too. They're very active. They will react with some metals and cause those metals to break down. Okay, and one way to test for them is what is called litmus paper. There's two types of litmus paper. There's a red and a blue, and it's simply just a check. It doesn't tell you the strength of the acidity. It just tells you whether it's an acid or a base. So if we take some blue litmus paper and we immerse it in an acidic solution, it turns it red. And that's all it's telling you. Going from blue to red, it is classified as an acid. Okay. Now, bases. You might remember this polyatomic ion from the polyatomic ion table. It's the hydroxide, okay? And so compounds that when they dissociate and produce a hydroxide ion is defined as a base, okay? The acid is any compound that produces a proton. H plus is an acid. Okay. Now, they tend to have a very bitter taste. I don't recommend tasting them, but you may have, let me restate that. You may have taken a base, for example, Tums. Tums is a base, okay? And it has a chalky flavor, unless they are minted or put other flavors in it, but in itself it has a slightly bitter taste. If you put them on your finger or on your hand, they give you this soapy, slippery feeling on your fingertips. And that is not because of the chemical. It is because of the base itself actually breaking down the tissue of your skin tissue and making it slimy. So if you get in there, you feel that, wash your hands immediately. Especially if you at home, if you use something like a Drano or liquid plumber. Liquid plumber is a classic example of a base. It will, you put it in your drain for clogged drains. It will, if you get some in your hands, it'll feel slimy. That's because, again, your fingers are, yes, borax, a question. Lee asked about borax. Borax also is a base. Okay, it has basic character of it. So now, with respect to the litmus test, the red litmus paper placed in the solution of the base, it will make it blue. Okay, so blue for base. Good way to remember it. Okay. Now, there's two definitions of acids and bases, and we're going to talk about them. The first one is the Arrhenius definition, okay, of an acid and a base. And that definition simply states anything in solution, when we place it in solution, that dissociates to produce the proton. Okay, so the proton noted here is the H plus. And so hydrochloric acid, that is the HCl, it's called hydrochloric acid. If it was HBr, it'd be hydrobromic acid, or HF, hydrofluoric acid. Okay, it produces a proton, which by definition, by the Arrhenius definition, is an acid. Now, according to Arrhenius, what defines a base is anything that produces a hydroxide ion. And so Tums, for example, when you ingest that, will produce an hydroxide ion. Okay, I got a question. Yeah, well, lots of, Ali has a question. My comment says lots of liquid meds are an ACL. What happens with liquid, a lot of medications, is sometimes what they do is they treat that medication with an acid to form a salt to make it more soluble in solution. And sometimes they do put it in an acid solution, again, so they can able to dissolve whatever the medication or the material it's made up of. Okay, so from Arrhenius definition, anything that produces a hydroxide ion in solution is classified as a base. Okay, now here's your first type of chemical reaction that you're being introduced to. And there's eventually we're going to get, there's a whole chapter on chemical reactions. There's only 6 of them. And this is the first one. This is called a neutralization reaction. This is when you get an acid reacting with a base. And they react with each other and they neutralize each other. Okay? You take Tums because you have a little bit of acid problem. That Tums, which has the hydroxide ion, then reacts with the proton in your stomach to reduce the acidity content in your stomach. That's a neutralization reaction. And if you notice here, we have a reaction. First reaction, neutralization reaction. You have an acid, hydrochloric acid. You have a base, sodium hydroxide. Okay. Now the hydroxide and the proton react to form water. Okay. Let me restate that. The proton from the acid and the hydroxide from the base react to form water. Okay. You can try this at home. If you try a little vinegar and a little baking soda, sodium bicarbonate is a base, vinegar is an acid, and when you put them together, you get a lot of bubbling action going on, and that bubbling action is just simply carbon dioxide being emitted, but then you neutralize the acidity of the acetic acid and neutralize the basicity of the base. Okay. And so for a neutralization reaction, the two reactants are required is an acid in the base, and you always get as a product water, always there. Okay. What is left behind are just the salts, and those are the partners of the acid. So the partner of the hydrochloric acid is the chloride, the anion, okay? And the partner of the base was the sodium. Okay, sodium has a +1 charge, the chloride has a -1 charge, and they simply produce sodium chloride here. Now they themselves don't really are involved with the reaction. They're kind of spectators. All they do is just make sure the charges are balanced when the reaction proceeds. The main components of the reaction are the proton and the hydroxide to give you water. And they give you water and then the corresponding salt. And in this case, we tend to think salt and only think of sodium chloride, but remember a salt is nothing more than any ionic compound. It's a metal and a non-metal. We could have easily used potassium hydroxide to create potassium chloride. Okay. So, first reaction, neutralization reaction. I'll give you another one. If you drove someplace today in your vehicle, you drove in your car, you had gasoline, it's a combustion reaction. Okay. You took the fuel, you ignited it with oxygen, caused a reaction that exploded in your engine, force a piston to move down and transfer that energy eventually to the back wheel so you can move forward. It's a combustion reaction. We'll get to those in time. Okay, so the problem with Arrhenius definition is it was kind of limited. It didn't really define other potential bases and acids out there. Because there are examples of bases that have nothing to do with the hydroxide ion. Okay, so Bronsted-Lowry came up with their definition, which they share with Arrhenius reaction the fact that in both cases, their definition of an acid is something that either produces or loses a proton. Okay, and so again, we have the example of hydrochloric acid. And then where they differ is their definition of a base. A base is any molecule that will accept that proton. Now, what do I mean by accepting that proton? Well, if we think about it, let me make sure I get this lined up properly. If we look at ammonia, it didn't come out very well. Let me see if I can draw something here. If we look at ammonia and we did the Lewis dot structure on this, we will find that ammonia has those two lone pair on the nitrogen. And go back to the Lewis dot structures of ammonia, okay? They're just sitting there doing nothing really. They're sitting on the central atom, in this case is hydrogen. Now, the proton has that 1s orbital empty now. Okay. Remember in the first slide where it starts off 1s1? Well, when it loses that electron, that orbital is still there, but it's empty. And so those lone pair of the nitrogen can actually insert those electrons into the empty orbital of the hydrogen, which in effect creates the ammonium ion. You're familiar with the ammonium ion because it's on the polyatomic ion table, okay? And so the ammonia and the NH3 accepted the, let me see if I can draw it. I got a new toy here. I'm trying to make it work and it's not functioning properly. No. No. Okay. Let me clear that. I guess my new toy is not working. But if we look at the Lewis dot structure of the ammonium ion, which is right here, okay, we have the 4 hydrogens around the central atom of nitrogen. Okay, they're all bonded now. And because it tied up those lone pair that were in ammonia, now we got a positive charge on the NH4. Okay, so that forms the ammonium. And so the main point is this: for a Bronsted-Lowry definition of a base, it really needs a lone pair in the central atom. And what this did by this definition, it opened up a whole bunch of different compounds that now could be classified, and they were and now it encompasses a lot more bases than the Arrhenius definition that only needed, that stated the base is defined by anything that produces a hydroxide. So you can have a Bronsted-Lowry base and not have any hydroxide involved here. This also is neutralized because the ammonia did neutralize the proton from the hydrochloric acid. Okay, so a little side note, one way to get rid of the odor of ammonia is to treat it with a base like acetic acid or vinegar. You'll get the same result. It was a different type of salt that they were formed, but they will minimize the ammonium odor because ammonium odor is a lot more volatile. And you form a salt here, the ammonium salt, which is less volatile, and therefore the odor drops. Excuse me. Down at the bottom, it kind of shows you a space field model of what's going on with respect to the reaction. You have HCl denoted by the red, big red sphere, the golden hydrogen. And then here the ammonium ion now has 4 hydrogens attached to the central atom of nitrogen, and then you have the chloride. Okay, so the hydrochloric acid loses or produces the proton, then therefore defined as an acid, and the ammonia here, the NH3, gains the proton or neutralizes the proton. And it's defined as a Bronsted-Lowry base. It would not be defined as an Arrhenius base. And that's important to distinguish the two, because there's no hydroxide involved in this particular reaction. Okay. Now, earlier I said, well, we get an acid, we put it in the water, and then it dissociates. Well, not all of them dissociate 100%. A lot of them dissociate much less. So we're going to talk about strong acids and strong bases. And by what I mean by strong is those acids and those bases that when you're put in water, they essentially dissociate to 100%. Okay? So it makes it a very strong acid, very strong. For example, the hydrochloric acid is defined as a strong acid, okay? Compared to acetic acid or vinegar, which is a weak acid because it doesn't dissociate 100%. Some examples of strong acids are HCl, which I just mentioned. Another one is HNO3, which is called nitric acid. And then the last one is H2SO4, which is called sulfuric acid. Those are three examples of very strong acids. And again, strong meaning that they dissociate virtually up to 100%. Yeah. So I put two examples of strong bases, meaning they're very soluble in water because they dissociate 100%, are the example we did earlier with sodium hydroxide and potassium hydroxide. Very strong bases because they're 100% soluble in water. Now, what is that? How would I get to know that? Well, we're gonna get to that, but I'm gonna share with you again the periodic table. Okay, because if you look at the far bottom right corner, you see something that says solubility rules. Okay, we have two columns, left column and right column. And we're going to get to this, but very briefly, everything on the left is soluble, meaning that those particular salts would dissociate 100%, with the exception, a few exceptions that are noted there. But if you look at number 1, on the left column, you see the cation lithium, sodium, potassium, and ammonia. That's the cation. And anytime you see those four, the big four there, and they're bonded to whatever anion, those guys are 100% soluble, 100% soluble. So in this example we just did, you notice that we got potassium hydroxide and sodium hydroxide. The cations are part of the soluble group. So we got 100% solubility in solution. Okay. Now, when you write the reactions, on the left is the reactants, and to the right of the arrow, all the products. Show them. You can see how they're shown there. They're shown with their particular charge, whatever charge that would be, in this case, plus for sodium and negative for the hydroxide. And then the AQ, meaning that it's in an aqueous solution or a water solution. The same is true for the acid example on top. Now, how do we denote this in diagrams? Okay, well, take a look at the diagram on the left that represents a beaker full of hydrochloric acid. We just stated that hydrochloric acid is a strong acid. So once it's in the water, it dissociates completely into the ions. And so here you see 3 molecules of hydrochloric acid all completely dissociated. So you may be asked to draw diagrams. Well, if you do, that's how you would show a strong acid. Don't forget the charges, okay? And if you use 3 molecules, make sure you got 3 positives and 3 negatives. You gotta balance the charges. On the far right is a beaker representation of a strong base. Again, 100% soluble. And so all the ions are separated. Don't forget the charges. And again, if I use 3, in this case, there's 3 molecules of sodium hydroxide I started off with, I'm going to end up with 3 sodiums and 3 hydroxides. Now, whether you draw all the hydroxides out or you put a hydroxide and put a 3 in front of it, that's fine. You can do it that way. That's acceptable, but that does, let me demonstrate what I mean. In that beaker, I could either draw each one separately, or I can put them all like this and just say, okay, I got three protons and 3 hydroxides. That's perfectly acceptable within that beaker, okay? Same is true for hydrochloric acid on the left. Okay, so of the 3 acids, we got hydrochloric acid and nitric acid and sulfuric acid, very strong acids. The bases are sodium hydroxide and potassium hydroxide. Okay. Again, what does strong mean? Simply put, it just dissociates to approximately 100% in an aqueous solution. Okay, and again, depending on what they are, if it's an acid, you're going to produce the proton ions and the counter anion, whatever that may be. Now, we also have what are classified as weak acids and weak bases. These are examples of compounds that do not dissociate 100%. They dissociate maybe 1 to 5%. Okay, and so that means that you still have intact the molecule. So we represent that by this chemical reaction with a slight difference in that in the previous examples we had a one-way arrow. Okay, notice here we have a two-way arrow. It just meaning it can go to the left as much as it can go to the right. And so this is the formula for vinegar or acetic acid, general formula. And we have here, this is acetic acid, okay? You'll see the proton will be written up front to designate to tell you, okay, I got an acid here. It will dissociate to give you the proton and the corresponding, what is called the acetate ion. Now, where's that acetate ion? I direct you back to the periodic table. And guess where it's at? Oh, right here. The acetate ion. So it dissociates to give you the acetate ion, and it is not 100%, so we use a double arrow. Some examples of weak acids are HF, which is hydrofluoric acid, not to be confused with hydrochloric acid, which is strong acid, okay? Remember that the fluorine or the fluoride has the highest electronegativity, and so it's not going to release that proton very well because that bond is pretty tough, okay? So it kind of holds on to that proton pretty strongly. So it results in having being a weak acid. You may be familiar with hydrofluoric acid if you ever do any type of staining of glass. Hydrofluoric acid is an acid that is used to stain glass. Okay. Now this you may be familiar with because you probably drink like I do in my soda pop. If you take carbon dioxide and bubble it through water, you make a carbonated drink. And one of the products that you make is carbonic acid. Okay, it has two protons when it dissociates. And then again, we have the general formula here, which is acetic acid. And then this last example, H3PO4. Again, if you drink a lot of soda pop, you drink a lot of that, that's called phosphoric acid. Okay? Phosphoric acid. So weak meaning that they do not dissociate 100% compared to the strong acids and bases that dissociate 100%. Now, how do we denote these in a diagram? Well, if you look at the beaker on the left, okay, we just told you that hydrofluoric acid is a weak acid. So to show that on the diagram, we show some ions, not a lot, just a few, maybe one, two at the most, that are in ionic form, okay, like that, okay? It still dissociates, but that demonstrates that there's not as much. And remember when we did hydrochloric acid, all of them are ions. Here, if we're gonna show 4 or 5 molecules, we have to show the rest of them is still combined. They're not dissociated, okay? And that is a representation of a weak acid. And hydrochloric acid happens to be a liquid, so it would be in solution, okay, but not dissociated. An example of a weak base is magnesium hydroxide. Okay? Magnesium hydroxide. Now, how do we know that that is a weak base? Well, let me very quickly go back to the infamous periodic table and direct you to the solubility rules down here at the bottom. So at your leisure, take a look at these, but if you look in the right column, that is generally insoluble. That's the insoluble column. And if you look at number 10, it tells you there that the hydroxide ion is insoluble because it's in the insoluble column, with the exception of 3, calcium, strontium, and barium. Those guys are soluble. Now, when they mean insoluble, it's telling you, yes, they're not going to dissociate, but because they're ionic, a little bit of it will dissociate. Therefore, it's a weak base. Okay? Weak base. So how do we demonstrate that in a beaker? Well, because it's a weak base, it's labeled insoluble. Doesn't mean it's 100% insoluble. I got to emphasize that. It means maybe one set of compounds would demonstrate, put them in ionic form to demonstrate that, yes, there's a little bit in solution. And so those are denoted here, okay? The ions of magnesium hydroxide. Notice I have 2 hydroxides. Why do I have 2? Because the formula for magnesium hydroxide, there's the parentheses, the polyatomic ion, there's 2. So there's 2 hydroxides. So I have to show 2 hydroxides in solution in ionic form. The bulk of the other material is still solid, okay? And we kind of make a little mountain here in the bottom of the beaker to demonstrate that they're still together, and it's what we call a precipitate. It's still it's out of solution, and it just settles to the bottom of the beaker. Okay? The bottom of the beaker. All right, so this is how we show with diagrams. On the left, a weak acid, and on the right, a weak base.
Can I ask a quick question?
Okay, some examples I just mentioned to you: HF, the weak acids, hydrofluoric acid, carbonic acid, phosphoric acid, and acetic acid. So we have 4 examples for you to remember that are classified as weak acids. And the weak base is magnesium hydroxide. Okay.
Dr. Fred,
Yes.
Amanda Bell was asking a question, but I don't think her microphone is working on your end.
No, I didn't hear her. Amanda, you want to try ask your question?
Yeah, on the previous slide, like when you were showing
you're
how
breaking up.
you were showing how with the magnesium hydroxide,
Yeah.
how it shows on a lump at the bottom. Is that because of its compound being it having metal?
But no, it's because it's insoluble. Okay, so you have a solid material.
The reason I was asking that is because of the one that you have on the left too. You don't have that doing the same thing. So that's why I was wondering.
Right, because on the left, it's a liquid. And so it's in solution. On the right represents a solid that did not dissolve.
Okay, all right, gotcha.
Does that make sense?
Yep, all right, thank you.
Okay, sure, no problem. You know, sometimes, I don't know if it's my connection. I did check my connections, but if you have a question, feel free to, if I don't hear you, type it in, because I do see my chat light up. I can look at it real quick. Sometimes I hear when you have a question, it's very clear, and other times it kind of breaks up every other letter. And for some of you, it's no breakup. For some, there is breakup. I don't know if it's our connection or what's going on here. Yeah. If you have a question, feel free to ask. Don't hesitate. One way or the other. Write it or speak it. Okay, so we had the weak acids. All of these are liquids. And so if we were to show them in the diagram, we would show them like that with the HF kind of in solution there floating around. Okay, now these guys, because it's an ionic compound, okay, would be solids. And therefore we would have to to show them, we would, okay. Oh, okay, I understand. Yeah, Amanda, no problem. Okay. All right, so the fact that we have a metal ionic compound would tell you that it would be a solid. Notice that the weak acids, they're all covalent compounds, but they're acids. So those guys will be liquids, okay? Will be liquids. So that's why you saw the HF kind of floating around in the beaker and the magnesium hydroxide drop into the bottom. And again, by weakness, we mean strength or how much of the ions went into solution. Being weak, not very many. Okay,
So you're saying the weak bases are metal compounds?
yes, the weak bases that you be dealing with would be ionic compounds, which is a
Okay, thank
metal
you.
and a non-metal.
All right, thanks.
Okay. Now here we have a question that you might be asked or something similar. We're asking you just by looking at the diagram, try to figure out, well, which one would represent a strong acid and which would represent a weak acid, and then which would represent a base. Okay. Now, the first one says a strong acid. So by definition, a strong acid, one, produces a proton, be it Arrhenius definition or even the Bronsted-Lowry definition. And so that's step one. And it looks like A, B, and C all produce protons. So we got an acid working here. Okay. And then the next step is strong. And then by definition, to demonstrate that they are a strong acid, everybody's an ionic form. And so of the A, B, C, it looks like only A, everybody's an ionic form. You got that A, which whatever A may be, negative, and everybody's dissociated. So A would represent a very strong acid, okay? If we look at B and C, you see that H and A are still combined. We have some examples of H and A still combined, but we have protons and the corresponding anion in solution. So that would represent a very weak acid. And then D doesn't really tell you much. It just HA, there's no protons in solution, so we have no acid, and there's no hydroxides in solution, so that wouldn't represent, that could be anything. That could be carbon dioxide. Carbon dioxide solution is basically just gas that's in liquid. It hasn't really dissolved, it's sitting in there. And so of that, A would be strong, B and C would be weak, and D can be anything. Okay. Now, of B and C, could I distinguish which one would be stronger? So they're both weak. Do I have a way to determine from the diagram that one would be stronger than the other?
Look to see how many protons there are.
Who would be stronger as far as an acid is concerned, B or C? We're just talking about B and C. B? Okay. That makes sense, right? Why would B be stronger?
Because B has more protons that are dissociated.
B has more protons. You cut out on the last part, but B has more protons. B has, it looks like 2 protons, and C only has 1. And so, though they're both weak, B will be a little bit stronger, okay? And you'll find that the case when we talk about pH, the pH scale. There is a scale of pH, and there's some weak acids are a little bit stronger than others. So we don't have a base here. We have nothing to deal with the hydroxide or even the Bronsted-Lowry definition. Okay, here's a scale of pH. The scale runs from 0 to 14, 0 on the far left, okay? neutral is 7. Okay. So your stomach acid is somewhere in the 1 to 2 range. So it's very acidic. And liquid plumber can run somewhere in the 11 to 12 range. Very basic. Okay. Water is 7. Now, let me ask you a question, because I see a lot of this out in the market. And there's a bottle out there that they call it alkaline water. Anybody by chance drink that? I tried it a few times. Okay. So alkaline water means that it's basic. So basic and alkaline are the same analogies. Acidic or acidity is something that has a pH. Anything that has a pH less than 7 is acidic. Anything that has a pH greater than 7 is basic or has alkaline nature to it. And there's a strength, either weak or strong, all the way to depending on where they sit in the scale. And so when you drink that alkaline water, it's, I believe, somewhere about 8 or 9 pH. Okay, not too strong. But then it goes into your stomach and it reacts with the acid in your stomach. So in effect, what has happened to the alkaline water that you drank, given what you know now about that reaction?
Well, when your stomach
Someone
acid
mentioned something, but they got cut out. What happens?
wouldn't your stomach acid just neutralize it?
Exactly. Okay, because back to the neutralization, your alkaline water has a base hydroxide in it. Your stomach has the acid, so you in effect have neutralized your alkaline water that you drank, okay, and created salts. And so, because your acid is your acid is pretty strong, it can take a lot of base. Now, you don't want to drink too much base because you don't want to change the acidity or the pH in your stomach, because a lot of enzymes in our stomach need that low pH because that affects their configuration. And that configuration is changed, those enzymes cannot help digest and break down whatever you ingested. So we're going to be careful with the pH of your stomach. You want to maintain it where it should be. Okay. Now down at the bottom, they introduce this brackets. Okay. These brackets represent what are called concentration. And so what we have here are the brackets, and that is concentration. Now it's a specific concentration, and it's introducing this to you a little bit early, okay? But those units, they have specific units, and we call that moles per liter. Now, I know you know liters, but moles is something different. It's a number that we're going to get into with time. So right now, that represents the units moles per liter, okay? Moles is simply a number. It just happens to be a big, big number. Refresh your memory in scientific notation because it will be using it when we deal with moles. 6.02 times 10 to the 23rd. That's how big 1 mole is, a very big number, okay? And so what this is saying here, the way they write it, is that when the concentration of the proton is greater than the concentration of the hydroxide, then it's acidic, okay? When the proton concentration equals a hydroxide concentration, we are neutral. And then when we pass the neutral range, the hydroxide, when the concentration of hydroxide compound, or in this case, polyatomic ion, is greater than the proton, then we're in the basic range, okay? So that's what that means there, those brackets. Now, I just mentioned to you that that bracket represents moles per liter of the proton concentration. Let me clear this up here real quick. And this just goes over again what we just mentioned, that when the proton concentration is greater than hydroxide concentration, then it's acidic in nature. And when the proton concentration is less than hydroxide, then it's basic, okay? Or when the hydroxide is greater than the proton, it's basic. You can read that one or two ways, just flip it over, it's the same thing. Now, I know you put your calculator away, but you may want to bring it back. Okay. Now, on your calculator, there's a button called the log, L-O-G. Okay. And we're not going to get into a lot of detail about this, but simply put, is if you take the concentration of your proton, get its concentration, and you type in log, you push the log button, you end up with a negative number, okay? And notice there's a negative in front of the log. That simply says that whatever the log of the hydrogen ion concentration is, you multiply it by a negative number. The point being that you always will get a positive number. So the log of the concentration will end up with a negative number. You can try that on your calculator and see how that works. So for example, something that has a concentration of 1 times 10 to the negative 1 or 0.1, and you hit the log button, you will get a negative 1 number. You multiply that by negative, that gives you a positive number. So the pH would be 1. Okay? So 0.1 would give you a pH of 1. Now, something at 1 times 10 to the negative 5th, take the log of that, guess what you get? 5. We're moving up the pH scale. Okay? You can notice the numbers. We started with 0.1 moles per liter. Now we're point and then 4 decimal places in the 1. Concentration gets smaller. We're moving up in. You might check, Amanda, you might check, it could be a second function. Okay, so it would be listed as LOG. Most calculators will have that.
I have an in log button, but it only when I press that, it just says in with a parentheses, and then it wants me to type something else in.
Okay, if you take, if you push the log button and then you type in that number 0.1 and hit equal, you should come up with a negative 1.
Yeah, I don't think that's the right button.
Okay. So
Because I typed that, and you said type in 0.1.
Okay. For example, let me share with you my calculator, well, the Windows calculator. And so if I type 0.1 and I hit the log, in this case, the log's sitting there, I end up with negative 1. And that times negative 1 gives me a positive 1. Okay. So if I type in 0.0005, for example, that's the concentration, I hit the log, that gives me a pH of 3.3.
Yeah, I may have to get a new calculator. My calculator doesn't have it. I have the Texas Instruments 36X Pro, and I don't have that button.
Okay, well, shoot a picture of your calculator and I'll take a look at it. I'm pretty sure you have that based on the model that you have. Okay. All right. So here, 10 to the negative 8, what would be the pH here?
That will be 8.
Anybody want to take a, given the trend, 10 to the negative 5th gave me a pH of 5, what would be 10 to the negative 8?
8.
You got it. 10 to the negative 3rd will give you a pH. Now, these are nice whole numbers, but if you use different numbers, you will get, obviously, decimal numbers, like the example I just did. Okay, but if this is 1 times 10 to the negative third, then I get a pH of 3. Okay, which will be written either in scientific notation 1 times 10 to the negative third, or write it out long ways 0.001, the same number. Okay, and then this one here would be pH of 8. So written out with all those decimal numbers, or written out as 1 times 10 to the negative 8, same number. So you can notice the concentration of the proton gets smaller and smaller, the pH goes up. It goes into the alkaline range. Now, what kind of pH value, so you can have a reference point? You know, if you have fish at home, you're probably checking the pH, because some fish requires very specific pH range. Okay, or you have swimming pool, same thing with swimming pool. But vomit, for example, has a very low pH, you know, roughly about 2, obviously because we have hydrochloric acid in our stomach. Lemon juice around 2.3, coffee a little bit acidic, maybe about 5 to 6, but it depends on the coffee. Saliva can range, it depends on what you've eaten or what you eat, but it's around 7. Blood, very important. Blood pH is very important. It's on the average 7.4, but there's a range of 7.2, I believe, about 7.4 that we must maintain. Otherwise, we have all kinds of trouble with our blood system. Milk and magnesia, pretty high. Alkaline solution, about 10.5. Ammonia, very high, about 12. Urine, that depends on, you know, your diet, obviously. And most soda pops, colas can range from 2.5 to about 3, 3.5, very acidic. I was surprised with root beer being a little bit more alkaline, about 5.5, but still acidic. Okay, so that is what kind of give you an idea when we talk about the pH. And pH is nothing more than a mathematical number of the proton concentration, okay? And the range goes from 0 to 14, with 7 being neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. Okay? Now we have what we call buffers. Now all they do, buffers, a very crucial buffer in your blood. It's, like I said earlier, blood has to maintain that pH, and we use internally a buffer system, and all that buffer system does is tries to maintain whatever pH you're trying to maintain. We can set up buffers for the whole pH scale from 1 to 14, and we can set that up. And what that happens is, if your blood gets too acidic, then it reacts with the base of your buffer to bring the pH back to where it wants it to be. Or if your blood gets too basic, it reacts with the acid part of your buffer to maintain that pH. So it's trying to maintain that pH. But you know, it can only work for a certain amount. You can't overpower the buffer solution, so you're kind of limited. It won't last forever, I should say. All right, now here we have a chemical reaction. It's one of your first chemical reactions that you work with. Now, in general, with the exception of H2O, otherwise water, where when we write water, we say H2O, hydrogen is always written up front. So that's the only exception to this general rule I'm going to give you. That when you see something written and the first thing you see is the hydrogen, okay, then 99% of the time you can say I'm dealing with an acid. In this case, this is nitric acid. Okay? Now, going over to the calcium compound, well, we got a parentheses. Okay, that should indicate to you I got a polyatomic ion, specifically the OH polyatomic ion, which is the hydroxide, which by definition is base because Arrhenius definition says anything that produces a base is classified as, excuse me, anything that produces hydroxide is classified as a base. So calcium hydroxide, I think, is the active ingredient in tons, by the way. One of them is the base. Nitric acid is the acid, okay? And when we have an acid in the base, we always produce water. We're neutralizing it, okay? Now you might figure, here's an introduction now to balancing reactions. What does that mean by balancing reactions? Well, one of the basic laws of science is conservation of matter, in that if I start off with 10 carbons as a reactant, I'm going to end up with 10 carbons as a product. They're going to be in different form, but I will have 10 products, 10 carbons. So for any reaction, I have to balance the atoms from reactants to products. They're going to be in different forms. For example, the proton from the nitric acid reacts with the hydroxide to form now water. So that hydrogen, which was in the acid, now is part of water. It's still hydrogen, but it's in a different form. Okay, we put a 2 in front of the nitric acid because we need to balance the numbers of hydrogens throughout this reaction. Because there's 2 coming from nitric acid, 2 hydrogens, and there's 2 hydrogens coming from a hydroxide, okay, which gives me a total of 4 hydrogens. And so when I put a 2 in front of water, I now have 4 hydrogens. So the hydrogens are balanced. We have made Mother Nature happy, okay? That's an example of conservation of matter. If we look at the calcium, we have 1 calcium atom in the form of calcium hydroxide, but after the reaction, we now have 1 calcium atom in the form of calcium nitrate. Okay, again, balance. All right, now the nitrate, which is the NO3, well, there's 2 of them in nitric acid. And guess what? We got 2 of them after the fact, after the reaction, okay? Because now calcium nitrate, we got the parentheses around the nitrate. All right, so in this example, the nitric acid is the Arrhenius acid because it, when it went in solution, it gives the proton. Okay. Well, I'll go through it one more time when I finish this, Amanda. Okay. And the calcium hydroxide, because it produces the hydroxide polyatomic ion, is the base. Right? So let me go back and clear that. So we make sure that we recognize, okay. Like I mentioned earlier, when we write a formula, you see hydrogen up front as the first atom written up front. 9 times out of 10, especially here 130, you can guess, unless it's H2O, you can pretty be assured that it's probably an acid. Okay? So the HNO3, you recognize that formula as one of the acids we talked about earlier. That's called nitric acid. And if we look over to calcium hydroxide, we see OH in the parentheses. Now, again, by definition, anything that produces a hydroxide ion is a base. And so we have an example here of an acid, nitric acid, reacting with the base, calcium hydroxide. We have an acid-base reaction. Okay? And in any acid-base reaction or neutralization reaction, we have water. That's the whole final product of an acid in the base. You're neutralizing the acid in the base to form water. Water is a neutral species here, okay? And so when you see the reaction, look for the proton, look for the hydroxide. Yeah, indicates neutralization reaction. Means I'm going to get water. Now, the reason we balance this is, again, because of conservation of matter. We have to balance all the atoms in the reaction. Now, we're going to get a lot more examples when we start balancing reactions. It's not next chapter, I believe it's the chapter after that. So in the meantime, for right now, that 2 up front tells you I need 2 nitric acids, okay? Because I need to balance the water that I'm going to make. I'm going to balance the hydrogens. I got 2 hydrogens coming from the nitric acid and 2 hydrogens coming from the hydroxide. That's a total of 4 hydrogens. They are in different forms, but that is 4 hydrogens. So if I start off with 4 hydrogens as reactants, I must have 4 hydrogens as products. And here, they're now in the form of water. So that's why there's a 2 in front of H2O. But we're gonna get more examples in a second. So right now I'm just introducing the concept of conservation of matter and energy. We'll get into that too. And so therefore we need to balance chemical equations. Now, why do I need to balance chemical equations? Because now I read that equation that tells me that for every 2 molecules of nitric acid, guess what? I only need 1. Remember, there's no number in front of calcium hydroxide. It's understood to be 1. And so I need 1 molecule of calcium hydroxide. So I got a ratio here, 2 to 1. So if I start off with 4 nitric acids, I need 2 calcium hydroxides. That is a constant ratio. I'm going to need that ratio when I start doing calculations, because when we get down the road, you'll be given, okay, if I start off with 10 grams of nitric acid, how much water am I going to make? And you need that ratio to get you from nitric acid to water. And to get that ratio, we're going to learn how to balance chemical reactions. Okay. Give me 1 second. I want to pull up. Bear with me for a moment. I need to look at something. Okay. Let me go over this conservation matter, why this is important. Okay, just very quickly. We're going to call this the atom life cycle. Okay. Let's take some picture of this grass here. Let's see if there is a way we can mark one particular carbon in one of those blades of grass. We're going to mark it so we keep track of it. Okay. Well, what happens with grass? Well, who eats grass? Okay. Cows. Well, cows have now ingested that grass. Okay. And that particular carbon now is incorporated into that cow by some means, tissue, muscle fiber, whatever case it would be. Now, my apologies to vegetarians, my partners are vegetarians, if you didn't like this file, but I'm just trying to demonstrate something, because now the carbon that was in the grass that got into the cow is now put into a human. Okay, and now it incorporates that same carbon that we marked way in the beginning into our body, into this gentleman's body here in that picture. Well, one of the byproducts that we have is what do we exhale? Carbon dioxide. So that carbon in the metabolism of that young man there may have been metabolized to create now, it could have been part of his muscle fiber, but now it's now created into carbon dioxide, and he exhales it. So that same carbon that was in the grass is exhaled, and it goes into the atmosphere. And then the cycle repeats itself. Plants absorb carbon dioxide, it incorporates it into its system, and that same carbon that we started off in that blade of grass has now made its full cycle back. Now, I may have, at one point in time, something to think about, I may have in me some carbon atoms that you may have had at one point in time in you. And your carbon went into the grass, it went into, maybe I ate the salad or something like that and incorporated into my system. But all matter, this is the conservation of matter. All the atoms remain the same, they just get converted into a different form. And therefore, we need to balance chemical reactions when we write the chemical reactions. So, does this diagram kind of help out as far as what I was attempting to do with respect to balancing the reactions? Okay, and we're going to get a lot more of that here fairly soon. All right, so nitric acid is the Arrhenius acid, and calcium hydroxide is the base, the Arrhenius base. Now, the question is, why do we bond two nitrates? Well, think about it. Calcium is a +2 ion. Remember, it's in group 2. The nitrates are -1 ion, polyatomic ion. So we need 2 of them to balance out the +2 from calcium. Okay. Now, in this example here, they're asking you to draw pictures of nitric acid, hydrofluoric acid, potassium hydroxide, and magnesium hydroxide. Some of these that we already talked about. Okay. So the first one is nitric acid. Well, we know from the list that we talked about earlier that nitric acid is a strong acid. So you have to determine first, is it a strong acid or base, or is it a weak acid or base? Okay, because once I know that, I know what type of diagram I need to draw. Nitric acid is a strong acid. Okay, so therefore, when I draw this acid to be represented in some solution, I need to draw it with the ions totally separated, and also with making sure that I have equal amounts of cations and anions. So in this case here, I got 3 protons and 3 nitrates. So that represents nitric acid. Hydrofluoric acid was one of the acids that they're classified as weak. And so I still need to draw a couple of ions together in there because it's weak, and even though it's weak, it means that there's still some ions in solution. Okay. But the rest of them are still intact. So HF represents the molecule still intact, and the proton and the fluoride represents the few ions that are in solution. Now, if I had a little instrument here, and they make these instruments, they're called conductivity. You've seen this commercial where they're comparing water, how to get rid of minerals out of water to different products, and they have a little instrument that immerse in the water, and they give you a measurement. That's called a conductivity. So if you have no ions in solution, you got 100% pure water, when you put that instrument, you would get no signal because it doesn't, no ions to conduct electricity. Now, the moment I put ions in solution, if I have a lot of ions, you get a very strong number. But if you have a little bit of ions, your number or your value would be much less. So if I had a conductivity instrument and I stuck it in that first beaker, it would give me a high number, or maybe have an LED readout where the LED would be very bright. The second example, the LED would read out, but it would be a very weak signal because there's not enough ions in solution. Okay? they're the ones conducting electricity. Those ions in your body that we carry 24/7 are very crucial. That's why, yes, you got to hydrate yourself. You're out there working out and it's hot. But not only that, you have to intake some salts, because even though you're hydrating yourself, you don't have enough ions. The nerve connections, the signals that are going through your body are not going to be there. So you got to make sure you are drinking things like Gatorade, and they're full of ions. And I can't think of the baby solution for babies offhand, but that's a good source of ions and water. Now, calcium hydroxide, the next one, is a strong base. So therefore, if we write a diagram, being a strong base, by definition, all my ions are separated, okay? And then finally, the last one, magnesium hydroxide. I gave you a list of, 4-minute warning, thank you. I gave you the list of weak bases, but if you're not sure, okay, we go to the solubility rules. And here in the right column, their insoluble column, you see number 10 in the bottom says hydroxides are insoluble, except those 3, which are soluble. The fact that it's in the insoluble column tells you it's going to be a weak base. Even though it's classified as insoluble, it's ionic, and some ions are still in solution. And so we have to show some ions in solution. And with that instrument, again, our LED readout will be very weak signal. In the bulk of the material, because it's insoluble, would settle to the bottom as a solid material. Okay. Unlike the HF, which is a liquid and just be floating around in solution. Okay, so let me summarize here, and then we'll call it a weekend. How's that? Call it a week. Okay, Arrhenius acids make ions when we put them in water. Okay, the bases, Arrhenius base produces a hydroxide in water. Now, with respect to the other definition, Bronsted-Lowry, a Bronsted-Lowry acid produces or loses a proton. You know, tomato, either way, a proton's involved. Okay. Where they differ in definition is the Bronsted-Lowry is that compound that gains or reacts with that proton. Okay. The Bronsted-Lowry opened up the number of different types of compounds that could be classified as a base. Strong acids and strong acids, they ionize or dissociate approximately 100%. Okay, so with that conductivity measuring tool, it was a very strong signal. Weak acids do not, much less, maybe 5%, 1 to 5%. It varies from the compound. But again, that conductivity tool will give us a weak signal. There's some ions in solution, but it'll be weak. Strong base, like the strong acids, dissociate 100%. And the weak ones, like the weak bases, the weak acids, much less. Okay? And buffers, their sole function is to maintain a pH constant, whatever that pH is. All right? So, with that in mind, let me mark where we're done. And I will stop it